All right, so continuing on in Unit 10 Geometry, we're going to start looking at area and the formulas for area for different polygons. Now, this is TEK 68B, and I'm going to read it in context. This is part of expressions, equations, and relationships. The student applies mathematical process standards to use geometry to represent relationships and solve problems. The student is expected to model area formulas for parallelograms, trapezoids, and triangles by decomposing and rearranging parts of these shapes. So we're going to model, or we're going to show area formulas. So we're going to talk about how, not only just what are the formulas, but how these formulas came to be, how they work, why they work for parallelograms, trapezoids, and triangles. And we're going to do that by decomposing or breaking apart different polygons and then rearranging those parts to create these shapes. It's important, first off, to define area. And so in our textbook, area is defined as the number of square units needed to cover a surface. So in other words, and this is Mr. Ermenc's definition of area, the amount of stuff. Right, so just the amount of stuff that's inside a flat or a 2D object. So that's my definition there. The area is going to be the amount of stuff inside, right? So if I colored this whole thing in, that's the area. Or if I had, for example, a triangle, the area of the triangle is the amount of stuff in the triangle. It's all the inside of the triangle. That's the area. In third grade, we began looking at area because we looked at multiplication using area models, and we started working with area. In fourth grade, we calculated area of various rectangles. So you guys already know about area. This is not new. This is just review at this point. All right, but previously, we used length times width to find area. So we always knew that area was my length times my width. And that works for all rectangles because all rectangles have a length and a width. And so we could call this the length and we could call this the width. Or because my rectangle is the same, if I were to rotate it 90 degrees, I could call this the length and this the width. And it's going to be the same because 3 times 4 and 4 times 3 are going to give me the same product. I'll have the same area for all rectangles. So that was good for third and fourth grade. However, what about other polygons? Does this work? What about my triangle? Do I have a length and a width? Is this the length? Or is this the width? What is the width? Is this the width? Or what about this parallelogram? Is this the length? Is this the width? A trapezoid? Is this the length? Is this the length, right? Or is this the length? Because all three of these are different things. So I have 3 different sides that are 3 different measures. Which one is the length? Which one is the width? And which one is neither? Because I have a length and a width, and then I don't know, right? I have something else completely different. So I really don't know how to talk about these other polygons in terms of length and width. And so because we need to extend our knowledge to other polygons, our knowledge of area, it is important that we begin using new vocabulary, and this new vocabulary we can use to describe the attributes of all these polygons. Now let's pause for a second and let's look at our star reference chart, or our MVP. What do we notice? Area, triangle, rectangle or parallelogram, trapezoid. I'm not seeing length times width anywhere. I don't see length times width. I don't see length times width. And I don't see length times width. Length times width is not there. So I find that kind of interesting. So that's what I learned. I learned that in third and fourth grade. And then all of a sudden, now if you look at the fifth grade MVP, it is there. It does say length times width. But in sixth grade, it doesn't. It's no longer there. So instead of calling it length and width, we now call it base and height. So we have some new terms. The first thing that we want to look at is we want to look at height. Height, I think, is the easiest to understand. Now, as we know, when we go to the doctor, or if we're at home with mom or wherever, Nurse Pretty, or just wherever we are, when we want to take our height, this is what we do, right? They say, stand diagonal, kind of lean over to the side, and then they measure your height, right? So that's what we do, is we take that and we say, okay, there's your height, right? No, of course not. That's ridiculous. We don't do that. It's never diagonal. Never that way. It's always straight up and down. If I were to talk about it in terms of the floor, so if this was the floor, my height, let me write that a little more straight. If that's the floor, my height is always going to be perpendicular to the floor. Always perpendicular, always a 90-degree angle. That's very, very important. Never ever is my height diagonal, right? So it doesn't make any sense. That's not the height. So height is always going to be perpendicular to what we're going to call the base. Base is always perpendicular to the height. Height is always perpendicular to the base. Always, always, always. So I'm never going to have a base like this and a height like this. That will never happen, ever, ever. Always going to be perpendicular. Very, very important. That's going to be a 90-degree angle. So now, when I look at those original polygons that we looked at just a moment ago, I now can see, okay, well, in my rectangle, I have my height, and I have my base, and they form a 90-degree angle. What about my triangle? Can I do that? Well, remember, my triangle, it's not this slanty part, right? Because we take our height, it's not slanted. My height is always perpendicular to the floor or to my base. So this would now be my height, and this would now be my base. Now, and sometimes you might see the height drawn outside of the triangle, and then it'll have a dotted line going to it. That's perfectly fine if you see it that way. You're going to have your base and you're going to have your height perpendicular to one another. So it's a 90-degree angle. And let me finish that in. So here's my base and here is my height. Well, what about this parallelogram? Well, I can do the same thing. I can call this my base, and then just anywhere, it doesn't matter. I could do it here and call that my height. I could do it over here and call that my height. I could do it out this side and call that my height, right? Because the height is the same no matter where. I could right here in the middle, and that's perfectly fine. So any of these is fine. Typically, you're going to see a lot of it's going to look something like that, right? And so your height and your base. And then on a trapezoid, same type of thing. You're going to have your height. But on a trapezoid, if you remember, we talked about something very, very important with regards to trapezoids. We said that the bases of the trapezoids are always going to be the parallel sides, right? So I'm never ever going to say that this is a base or this is a base. That's not ever going to be the case. So my base are always going to be my parallel sides, and then I have my height. And we'll see why in just a few minutes. On my rectangle, it's important to note, just a side note, that this, I could call that my base because it's congruent to that, right? It's the same thing. I could call this my base because it's congruent to this. So my parallelograms, and again, rectangles and squares are parallelograms. So parallelograms, you could call either one. So they technically also have two bases, but you really only need one. Now for my trapezoid, I have two bases. And so we'll see why that's important here in a few minutes. But I have my bases and I have my height. All right, so hopefully this all makes sense so far. Hopefully I'm not losing you. If I do, feel free to pause, rewind just a little bit, back it up just a little bit and watch that part again. But it's pretty straightforward at this point. So now that everything makes sense, it's time to confuse you. Most of the time in math, I love math. I don't teach math because I'm good at it. I teach it because I enjoy it. I really, really do have an enjoyment for math. I love patterns. I love numbers. I just find them to be very, very fun. Now, there are certain things in math that I don't like. This is one of those things. So let's look at our MVP here for just a moment. couple of things that I want to point out. So I do have a base in my formula. B stands for base. Do not confuse this with this one. So capital B. Capital B is not the same thing as lowercase b. Capital B, and we'll talk about this next week, but capital B stands for base area. So already it's a little bit confusing, but that's not the end of the world. It's a little bit confusing that I have the same letter meaning two different things, but lowercase b is base, uppercase B is the base area. Okay, that's not too bad. I'm okay with that. I don't like it, but I'm okay with it. Now here's what I really dislike. So here I have height, height, and height. And so H stands for height. But height of what? Well, height of my triangle, my parallelogram, which a rectangle is a parallelogram, or height of my trapezoid. So this is my height of my 2D figure. So it's the height of my triangle, height of my rectangle or parallelogram, and the height of my trapezoid. Okay, that's not too bad, but this is where it gets stupid. Is now here I have height, but let me use a different color highlighter for this one. So, all right, so here I have height, and this height is not the same as these others. It is not the same thing, completely different. This height is the height of a rectangular prism or a 3D object. If we were in class, I would be able to kind of demonstrate this a little more. Don't worry too much about it. It's stupid, really. It's confusing because I have the same letter, meaning with the same word, height, but they're two completely different things. I have the height of my 2D object here, and I have my height of my 3D object here. And we'll talk more about what that is. Don't worry too much about this. So I have here, it says don't focus too much on the names of things, but rather focus on the concepts. So if you really focus and pay attention to the concepts, the names won't mess you up too bad. But if it was me, I would use a different variable. I would call it a different name. I would call it layers, honestly. And so when we do volume next week, you'll see why. But instead of calling it height of a rectangular prism, I would call it layers of a rectangular prism. That's just me. But I just wanted to kind of talk about vocabulary for just a second, and so we can kind of really see what is what. All right. So again, don't worry about it too much. Don't let it get you down. It's okay. It's going to be fine. All right. So your MVP has the formulas. You don't need to memorize them. But it is important to understand where these formulas come from, and it's also important to understand why they work. So we have our formulas, we see what they are, but I want to know, where does it come from? Why is this the formula for a triangle? Why is this the formula for a trapezoid? Why does it work? How does it work? I want to really understand what's going on here. So that's what we're going to do. Now, our textbook defines area as using square units, so we do need to talk about units for just a moment. Before we do that, or to introduce that, I want to talk about some patterns that we know in math that we talked about. So I could have also had the across disciplines within disciplines magnet as well. This is back when we first learned exponents. So 5 to the first power is just 5. Easy enough. 5 to the second power, or 5 squared, is 5 times 5, which we know is 25. 5 to the third power, or 5 cubed, is 5 times 5 times 5. And 5 times 5 is 25 times 5. So 25 times 5, or if I have 5 quarters, I have 125 cents, right? So 5 times 25 is 125. Okay, easy enough, not too bad. Now what we need to talk about is units. So if I had inches and I wanted to measure something going in one direction. So just a linear direction. There we go. I could talk about this in inches. I could say that this is 5 inches. I could talk about, let me draw this, and it's not going to be to scale. It's not going to match the previous one. Trying to save some space here. But let's say this is a square, and let's say that this is a 5 inches by 5 inches squared. So this would be 25 square inches. And what's important is that on the first example, I'm going in one direction. This is inches to the first power, or inches, right? So it's the same thing. Just like 5 to the first power is just 5, inches to the first power is just inches. It's just going in one direction. It's a one direction and one-dimensional object. Here, I'm going in 2 directions. I'm going in this direction and this direction, length and width, or base and height. And because I'm going in 2 directions, I have inches squared. So I'm going to be talking about square inches when I'm talking about area. And this is not only 2 directions, but I could say that this is 2 dimensions. So this is a 2-dimensional object. Now, as you might guess, and I'm really not good at drawing this, but I'm going to try my best. But if I were to draw a cube and say that that was a 5 inches by 5 inches by 5 inches, now this is going in 3 directions. I have a base width and a height, or a length, width, and a height, right? So I have 3 dimensions, and this would be a 3-dimension or 3-dimensional object, and this would be inches cubed. So what you need to know is anytime you see inches as your unit, you're talking about linear measurement. Anytime you see in a word problem square inches, you know you're talking about area. And anytime you see inches cubed, or cubic inches, or cubic units, we're talking about a 3-dimensional object, or talking about volume. Another thing that we can talk about is we can say, well, there's inches, cool, linear. Or I can have inches times inches, right? So I have inches times inches in my area model. So inches times inches is inches squared, or square inches. Or I could have inches times inches times inches, which is inches cubed, or cubic inches. So here, this is linear. This here is going to be a 2D, or area. And this is going to be 3D, or volume. So just kind of a little tip on if you see inches, linear, inches squared, area, inches cubed, or centimeters cubed, or whatever your unit of measure is, cubed, then it's going to be volume. All right, so we're going to look at now and how these formulas work, and decompose some shapes and be able to discover where these formulas come from, why they are what they are. And some materials that you're going to need: you need 4 index cards, you need a pencil, ruler, scissors, and if you have them, markers or colored pencils. Now, if you don't have these items, then that's fine. You can just watch me do it. I'm going to demonstrate, and I'm going to do the whole thing. But it's really more effective if you have these items and you can go step by step with me.